Introduction to Quantum Theory. PHY 102, Quantum Physics. Topic 4. Introduction to Quantum Theory. Wave functions. Significance of wave function. Normalization. The time-independent Schrödinger equation. Solutions of the TISE, the de Broglie hypothesis. In 1924, de Broglie suggested that if waves of wavelength lambda were associated with particles of momentum p equals h/lambda, then it should also work the other way round. A particle of mass m, moving with velocity v has momentum p given by kinetic energy of particle. If the de Broglie hypothesis is correct, then a stream of classical particles should show evidence of wave-like characteristics. Standing de Broglie waves, e.g. electron in a box, infinite potential well, V equals 0, V equals 0, V equals, electron rattles to and fro. Standing wave formed. Wavelengths of confined states. In general, K equals n/L, n equals number of antinodes in standing wave. Energies of confined states. Energies of confined states. Particle in a box, wave functions. From Lecture 4, Standing wave on a string has form. Our particle in a box wave functions represent stationary, time-independent, states, so we write A is a constant, to be determined. Interpretation of the wave function. The wave function of a particle is related to the probability density for finding the particle in a given region of space. Probability of finding particle between 10 and 10 plus dx. Probability of finding particle somewhere equals 1, so we have the normalization condition for the wave function. Interpretation of the wave function. Interpretation of the wave function. Normalization condition allows unknown constants in the wave function to be determined. For our particle in a box we have Wf. Since, in this case the particle is confined by infinite potential barriers, we know particle must be located between x equals 0 and x equals L. Normalization condition reduces to particle in a box, normalization of wave functions. Some points to note. So far we have only treated a very simple one-dimensional case of a particle in a completely confining potential. In general, we should be able to determine wave functions for a particle in all three dimensions and for potential energies of any value. Requires the development of a more sophisticated quantum mechanics based on the Schrödinger equation in one dimension. Time-independent. K-term. P-term. Solving the Schrödinger equation allows us to calculate particle wave functions for a wide range of situations, see Y2QM course. Finite potential well. WF leakage, particle has finite probability of being found in barrier, classically forbidden. Solving the Schrödinger equation allows us to calculate particle wave functions for a wide range of situations, see Y2QM course. Barrier penetration, tunneling. Quantum mechanics allows particles to travel through brick walls. Solving the SE for particle in an infinite potential well. So, for 0 less than x less than L, the time-independent SE reduces to general solution. Boundary condition, psi, x, equals 0 when x equals 0, b equals 0. Boundary condition, psi, x, equals 0 when x equals L. In agreement with the fitting waves in boxes treatment earlier. Molecular beam epitaxy, man-made potential wells for quantum mechanical engineering. Molecular beam epitaxy, man-made potential wells for quantum mechanical engineering. Quantum cascade laser, engineering with electron wave functions.